Hello everyone. This week we are talking about Anova, and we've talked about Anova a little bit before, but I'm going to go into it in a little bit more detail. A key thing to remember about Anova is the subtitle here, that we're comparing more than two means. And what that really means is that we are looking at a single variable, and we are looking at the mean of that variable across more than two groups. If we just have two groups, then we can use a t-test, which basically t-test and one-factor Anova with two groups is basically the same thing. But if we have more than two groups and we want to look, or more than two conditions, and we want to look at how a mean value changes across those conditions, that's where Anova comes in. So the simplest Anova is a one-factor independent measures Anova. So in that case, we're only looking at a single variable, and we're looking at how that variable changes over groups. If there are more than two groups, then of course we use Anova. If there are two groups, we use t-test. And the groups are independent. What that means is that when I am looking at a value, for example, I'm looking at average age, and I have four groups. If I'm looking at average age over four groups, those four groups are made up of individuals that are different from all of the individuals in the other four groups. In other words, there's no overlap. And that's what we use the term independent to define in a situation like an Anova, is where that groups are made up of entities or people or measures that are unique to that group. So what will Anova tell us? Well, the main thing that Anova tells us that amongst the three or more groups, remember that's to be at least three groups, two of the measures or two of the means are statistically different. That would be a positive outcome of an Anova. Of course, Anova could give us the opposite and tell us that none of the groups are different, and that would be, of course, one where we would not be able to reject the null. But assuming that there is significant difference between at least two of the groups, that's really what Anova tells us. What it doesn't tell us is it doesn't tell us which two of the groups are the ones that are different. And I'll get to that later and talk to you about how we figure that out. So here's an example. Assume that we have four classes. We call them Group 1, Group 2, Group 3, and Group 4. In Group 1, we give those students common math instruction for the entire year. In Group 2, we give them the common math instruction that the other group got, but we also add in a 3-month-long intervention intended to make their math skills stronger. In Group 3, they get the common math instruction, but this time they get a 6-month intervention. And in Group 4, they get the common math instruction, but they also get a 9-month intervention. So what we want to know is using Anova, that at the end of the year, when we administer the final math exam, say it's a standardized exam of some sort, are the average scores between the groups on that exam, are they statistically significantly different, or are they all the same? Because if they're statistically significantly different, then some level of intervention must have made a difference in the scores. If they're not, if the means are all the same, then we can conclude that there really was no intervention. The thing that's challenging about this is that we have three different levels of intervention. So we have 3 months, 6 months, and 9 months. And because Anova doesn't tell us where the difference lies, we can only presume that some groups are different. Again, later I'll talk about how we figure out which of the groups actually are the ones that are statistically significantly different. So our hypothesis is that the math intervention, our null hypothesis I should say, is that the math intervention did not make any significant difference in the average end-of-year math scores along the four groups. Our research hypothesis is that it did. The math intervention did make a significant difference in the average end-of-year math scores across the four groups. So the independent variable is going to be the intervention and the levels of intervention, whether it be 0 months, 3 months, 6 months, or 9 months. And the dependent variable is going to be math scores at the end of the year. Anova answers the question, is there a significant difference between at least two of these groups? It could be three groups that are statistically significantly different. It could be all four, but it's got to be at least two to get a positive result out of an Anova. Or is there no significant difference between the two, or at least two of the groups? And that basically means that the group means are the same. Each of the individual group averages is the same. So we're going to go ahead and run the Anova analysis. First, we're going to feed it in all of the scores and identify the groups, and then we'll run the Anova analysis and try to determine if we can reject the null hypothesis that there in fact is no statistically significant difference. So assume that our ANOVA returns a result that says there is a difference. So that difference might be between group 1 and group 4. And group 1, remember, had 0 months of the intervention, whereas group 4 had 9 months of the intervention. So that would be your most extreme difference. Okay? But at the same time, there could be significant differences between group 1 and group 3 and 4. In other words, 6 months and 9 months of the intervention actually had a statistically significant impact on the scores at the end of the year, whereas group 1 did not, or difference from group 1, I should say. To throw another monkey wrench in the works, the difference might be between groups 2 and 4, but not between 3 and 4 or 1 and 2. In other words, the intervention at 9 months had a much bigger impact than the intervention at 3 months. But the intervention at 3 months really wasn't statistically different from no intervention at all. And the intervention at 6 months wasn't really statistically different than the 9-month intervention. So this is where ANOVA kind of gets more complicated. But just assume that when we get our results back, we have a way of being able to determine if any of the two groups are different. And the way that we determine if any of the groups are different, and if the difference is actually real, is something called the F statistic. Now, I went through in another presentation a little bit about the F statistic, and I'm going to go through it again because it's worth knowing. But it's not life-changing. So if you don't understand the F statistic and you don't understand how it's calculated and what it means, that's fine. I'm going to go through this and just sort of explain it, but it's not something that you absolutely need to know. I will tell you what you absolutely need to know at the end of this. All right. Assume for a second, on my second bullet point there, assume for a second that there is no difference. The null hypothesis is true. There is no difference between any of the groups. Okay. In that situation, we are able to actually quantify the amount of variation, or the amount, what we call error, the amount of error. And if the null hypothesis is true, then we have quite a bit of error. We denote that as our total error, or the sum of the squares of the total. And sum of the squares is just the way that we actually calculate that. But just for this argument, it's our total amount of error that's actually in our experiment. And that's denoted with an SS lowercase t. If there is a difference, so let's assume we just made the assumption that the group means were the same, and that's how we calculated our sum of the squares for the total error. But now we come along and we're going to say, okay, well, let's assume that the research hypothesis is true and that there is some amount of that variation that can actually be accounted for when we assume that the group means are different. So we calculate what that is, and it's a subset or a part of the total error. That becomes our model error. So our model error, SSM, is what the ANOVA explains. Of the total error, the ANOVA can explain part of it, and that's the SSM portion. But also amongst the total error, the ANOVA can't explain everything. So there's going to be some unexplained error. That's denoted using SS residual, or SSR. And if you look at any ANOVA experiment, you will see that the SSM, the amount of variation the ANOVA can explain, plus the SSR, the amount of variation that ANOVA can't explain, equals SST. And that's a pretty hard and fast rule. That's basically, we're taking the total error and we're breaking it into two buckets. That which ANOVA can explain and that which ANOVA cannot explain. So really where the F statistic helps us is that if the explained error is bigger than the residual error, then it's likely we have a significantly different result. But there's more to it than that. This week, the book started talking about degrees of freedom. Actually, the last couple of weeks, it's talked about degrees of freedom. And degrees of freedom become a factor in determining our F statistic. So we take our error values, both the SSM and the SSR, and we divide each of them by their degrees of freedom. Well, how do we determine the degrees of freedom? Well, for the model, for the SSM, the degrees of freedom are the number of groups minus 1. So in our math example, we had 4 groups. So we would take away one of those, and we would have 3 degrees of freedom. So we would divide the error value by 3, distributing that error over those 3 degrees of freedom. And that's how we come up with something called the mean sum of the model. Okay? So MSM is the mean sum of the model. It's the value you get when you divide your SSM by your degrees of freedom. In a very similar way, we do the exact same thing with the residual. We figure out the degrees of freedom for the residual, and we divide SSR by that number of degrees of freedom. So the degrees of freedom is the number of participants in our experiment minus the number of groups. And there's a ton of literature if you want to look at why these things are the way they are, but just at this point in time, I'm going to ask you to trust me that they are the way they are. Anyway, moving on. Assume that we had 100 students in our math example. We had 4 groups of 25, and those were all independent measures. So our degrees of freedom in this case would be 100, our n is 100, minus 4 groups, or 96. So we're going to now distribute the residual error, the SSR, over 96 different degrees of freedom by dividing the SSR by 96. And the result is going to come up with something called the mean square residual. So when we are accounting for the degrees of freedom, 2 things happened. One, we came up using SSM, we came up with a mean square of the model, and that's when we distributed the amount of error over the degrees of freedom, which in that case was 3. And we came up with the mean square of the residual by distributing the sum of the square residual value over 96 degrees of freedom. All right, the final step is we calculate the F statistic by dividing the mean square of the model. Remember, that's your SSM divided by your degrees of freedom. And then we take that value and we divide it by the mean square of the residual. And in that case, it was your SSR divided by your 96 degrees of freedom. So the F statistic equals the mean square of the model divided by the mean square of the residual. And in plain terms, it's basically the explained error transformed a bit divided by the unexplained error. So you can imagine that if your F statistic has a great deal of explained error, then you're dividing that by the unexplained error, and it's a smaller value. That means that the Anova was able to account for more variation than it was not able to account for. And that's a very positive result. We get a higher F value there. However, if your mean square model is small, that probably is going to indicate that your mean square residual is going to be larger because there's more unexplained error than there is explained error. And that's going to cause your F statistic to be low. Okay, so I've got some explanation there. I show you that F equals MSM divided by MSR. What does that mean? And just as I've explained it here, if our mean square of the explained error is much larger than the mean square of the unexplained error, then the F value will be high. That's good. That means our Anova accounted for a good deal of the total error. There is a significant difference between at least 2 of the groups, and we can reject the null hypothesis and accept the research or the alternative hypothesis. However, if our mean square of the explained error is about the same, or not much larger than our mean square of the unexplained error, then the F value will be low, and that's not good. That means that the Anova really didn't account for very much. And the null is probably true, or there's enough reason to believe that the null is true, that there probably really is no difference between the groups. The reason why I go through all of this detail is because when you run an Anova, you're likely to see something that looks like this. And the F statistic will be part of your results. So let's go through what this is showing us. And I've got some notations in here, but they're really light. The SSM, SSR, and SST are white, and that's just a design I chose in PowerPoint, and I wish it wasn't like that. But anyway, so here's our results. We have what's noted as between groups. Well, I've designated that as model, and that is the difference between the groups. Okay. Then we look at the difference within the groups. That's if you've got 25 students in each group, how much variation is there within the groups? And that's our SSR. So the between groups, the Anova is designed to explain that. So we're looking at that. That's our SSM. What's the Anova able to account for? And in this particular case, it's 2.033. Within groups is just variation that the Anova isn't designed to account for, and it's not going to find things that are within groups because all it cares about is the differences between groups. That's SSR, and it's a much higher value. But that's okay that it's a much higher value because we're going to look at the degrees of freedom. Then we have the total error. That's the SST. And remember I told you that total error is always going to be the sum of SSM and SSR. What Anova is able to account for and what Anova is not able to account for becomes your total error. Next column over, we have our degrees of freedom. Between the groups, we're having to distribute 2.033 units of variation or error across 3 degrees of freedom. and we get 0.678. That becomes our mean square for the model, 0.678 value. Then within groups, we come over here, we have a much higher error value, but that's because we have so many more degrees of freedom. And so we have 542 degrees of freedom. We're going to distribute 123.504 across 542 degrees of freedom. That's going to give us our MSR, and that's going to be 0.228. Then we're going to take the final step. And the final step is we're going to calculate our F statistic. We do our calculation of our F statistic by taking 0.678 and dividing it by 0.228. And we come up with a value that is almost 3. And while that's not a great F statistic, it is still a high enough F statistic to suggest that the ANOVA did find a sufficient amount of variation between the groups in order for us to say there's something there. We also calculate a p-value, and that's our significance here. A p-value, if we were setting the p-value threshold to 0.05, this p-value is coming in under 0.05, and so we can say that we have a good level of confidence in our F statistic that indicates that our ANOVA uncovered a statistically significant difference between at least 2 of our groups. That's a lot of math stuff, okay? And it is. But for you who want to know how we measure the effect of an ANOVA, that's it. We measure it using the F statistic. So when you run ANOVA in SPSS or R or any of the other statistical packages, you're going to see an F statistic. And it's important for you to understand what that F statistic means. So the F statistic is going to tell you how much of the ANOVA, how much of the variation was the ANOVA able to account for relative to what it wasn't able to account for. And if the F value is high, that's good. But always look at the p-value, because there can be varying conditions where the F value can be high, but maybe the sample wasn't big enough, or there was some other factor, and the p-value comes up above 0.05, which means you can't really have a lot of confidence in your F statistic. All right. Promised I would tell you, once we figured out that we have 2 groups that are statistically significantly different, how do we know which ones they are? Well, sometimes you can run t-tests if you want to test each condition against each other, but that becomes problematic because that can give you some false positives. But there's a couple other ways, and I'm not going to go into too much detail about each of these. I just want to let you know. The book talks about them a little bit, but I want to let you know that they exist. So if we get a significant ANOVA result, how do we know which group comparisons are causing that? There are 2 ways. If we have an idea, for example, in our math example, if we thought that for group 1, where there's no intervention, is going to be statistically significantly different, the means are going to be statistically significantly different from group 4, then we could set up a planned contrast. And a planned contrast is where we actually do a 2-way comparison. We compare control to all 3 of the treateds. Then we remove control out. And we compare treatment 1 to the other 2 treatment conditions. Then we take treatment 1 out, and then lastly we compare treatment 2, I guess it would be group 3, to group 4. And so we go 2 by 2 and we figure out which ones are statistically significant. And the planned contrast will do that. And there are varying ways of doing planned contrast, but that's one way we can do it. If we really don't know, really have no idea, don't have any real hypothesis about what's going to be different, then we could run what's called a post hoc test. And a post hoc test will do exactly that. It will do a pairwise comparison of all of the groups, and it will return you a result that will show you, along with a p-value, it will show you what is significantly different. Why do we do planned contrasts as opposed to post hocs? Because planned contrasts are more accurate. Planned contrasts are a more careful way of being able to calculate this, whereas post hoc tests, many of the different versions of post hoc tests that you would run, are very susceptible to outliers, very susceptible to situations where the group means are not equal, very susceptible to situations where there's a lot of variation in the groups. So post hocs will get you kind of 80% of the way there, and sometimes the results are good enough, but really planned contrasts are the ones that when you set that up and the different ways that you do this, it's going to give you a much more accurate result. All right, so what I've talked about so far is one factor independent ANOVA. Remember, that is where we take one thing. What our example was we took the math test results and we checked to see if it was different across 4 groups. 4 groups of independent entities. In other words, there's no overlap between the groups. So there's a couple other types of ANOVA, and this is in your chapter on just general statistical tests where they like write basically a paragraph about each of these statistical tests. But you may run into them when you're doing your research, doing your lit reviews and stuff like that. You may run into these, and it'd be good to know what they are. They're basically the same thing. It's an ANOVA with a different flavor, and it's going to give you an F value, and you're going to be able to look at the F value and determine whether or not your results of your ANOVA are significant. So the first one is ANCOVA, and ANCOVA is where you use a covariate. Now, in our example, our math example, we just looked at the intervention, 3-month, 6-month, 9-month intervention. We just looked at that intervention. That's all we looked at. But imagine for a second that we could look at a different variable, right? There's another variable, and in this case, it could be a covariate, could be the student's experience with similar interventions done in the past. Let's assume in the previous academic year, there was a different type of intervention. Maybe it was math intervention. Maybe it was some other discipline intervention. But some students had it, some students didn't. And so that covariate is actually going to impact the extent to which students might perform given the intervention that they're doing this year. So it's just something that is kind of thrown in there that's going to impact the results. It typically will reduce your residual error. So if you have a lot of residual error and you can account for a covariate, you can reduce that residual error by accounting for some of it using your covariate. So that's what ANCOVA is. Multi-factor ANOVA is where you have more than one independent variable. In our case, our math example, we had one independent variable, and that was the intervention. But what if we wanted to look at other scores? And we're going to look like, for example, well, let's look at math, let's look at reading, and let's also look at the interaction between math and reading. So you could have two factors, you can have an unlimited number of factors. Of course, the complexity gets a lot higher the more factors that you have. But we could be looking at two things at the same time and seeing what the impact of variable A is, the impact of variable B, but a two-factor ANOVA is also going to give us the impact of variables A and B. Lastly, what we had done here was an independent ANOVA where the students in our groups were in no way overlapping. But sometimes you design an experiment where you're using the same students. So imagine that we had 25 kids and we were going to expose them to one experience, experience A, we're going to expose them to experience B, and we're going to expose them to experience C. And what we want to know is we want to know how much variation there is between the three experiences as opposed to how much variation there is between the individual kids, the 25 kids. That repeated measures ANOVA basically means that we're not independent, that we do have overlap in our groups, and that we're using the same kids for all three different conditions, and those things have to be accounted for when we actually run the tests. The other thing that's kind of a factor when we're looking at repeated measures ANOVA is that there can be test fatigue and test familiarity. So if we have 25 kids and we're going to expose them to three different conditions, by the time they get to the third condition, it may be impacted by the fact that they've gotten very used to what they're supposed to do in each of the different conditions. So we have to account for that as well. And that just can come into the way that the sample is selected or the sample is organized. So that is everything I'm going to tell you this week about ANOVA. That should help you answer the alternative assignment should you choose to do that for the discussion boards. If you're going to go ahead and do the original assignment, feel free to do that as well. Let me know if you have any questions.